Hello, everyone. So we're going to be talking about linear functions, and linear functions are really important in the world because they cover so many different areas, and being able to make a linear function helps with solving a lot of different kinds of problems that we have in this world. So I just have a few examples here that I can talk about. So like velocity is one of them. So you might say, well, if I'm going 60 miles per hour for 3 hours, well, how far am I going to travel, right? So you would just multiply 60 miles times 3 hours, 60 miles per hour times 3 hours, and you get 180 miles, right? Um, but of course, you want to be able to mix this up, so you want to be able to put in a new distance, new mile per hour, or a new time, right? So the relationship is the distance is equal to the rate times the time. So you might have seen that before. And so if any of these are fixed, so that means a constant. So if I'm going at a constant speed, so I could have the distance is equal to 60 miles per hour times the time. So this would be a linear relationship. And if I did a graph of this, it would always for every, for the first hour, I go 60 miles. For the second hour, I've gone 120 miles. For the third hour, I've gone 180 miles. And if you put that onto a graph, you would see that the points all line up in a straight line. So that's useful. Also, we have circumference and perimeter. Anytime we do a one-dimensional measure, that will come out into a linear type function. So if I wanted to measure the circumference of a circle, maybe you remember it was the circumference is 2 pi r. Well, if I wanted to look at one inch radius, right, I put in 1 for r. If I want to put a 2-inch radius, I put in 2 for r, and you would see that this all changes by multiplying by 2r each time. So the rate of change of this function would be linear, and it would be constant by the rate of 2 pi. So every time this would grow by the same amount, 2 pi. So for 1 inch it would be 2 pi. For 2 inches it would be 4 pi. For 3 inches it would be 6 pi, and so on. And also perimeter of any shape. If we have a single variable, if I grew this rectangle from 1 by 2, if this was x was 1 inch, and this was also the x would also have to be 1 inch, so this would be 1, and then 1 plus 1 is 2. So the perimeter of this would be 1 plus 1 plus 2 plus 2, so 4 plus 2 would be 6. And then if it was 2 inches on the side, then it would be 2 plus 2, which is 4, plus 6 plus 6, which is 3 plus 3, which is 6, so that would be a total of 10. So 1 would be 5, 2 would be 10, and it would go up at a constant rate, just like the circle would. So any one-dimensional measure is going to be a linear function. We like to use linear functions in statistics when we compare two quantities. Like I saw one just the other day. It was comparing how much the cost of a head of state's car, like the president, like how much his car costs versus how corrupt the government was. So they were trying to show that the more the car cost of the government head, the more corrupt the country was. And they had like Equatorial Guinea, and this guy had a crazy sports car, that was very expensive, and it had a very corrupt government. So but there was Norway had a very pretty open government that was not very corrupt, and also the head of state, he drove like a cheap car. So they were trying to show that it's kind of a linear relationship. So statistics use linear functions quite a bit. Cell phone charges, anytime you have a price per, there's a rate, right? Or this would be kind of the initial cost, $40 per month, plus 5 cents per minute or something like that. So every minute, that you spend on the phone, it increases, but it would be a linear relationship. That it it changes by how many minutes you go. Each one minute would cost you 5 cents on top of the $40, right? So that's a linear relationship. Cost, if I have $25, how many widgets can I buy for $1.50? So that would be like you start with an amount and then you are going down by $1.50 for each thing that you want to buy. So this would be a linear relationship, constant rate of change. Counting supplies, so like if you had a bunch of shelves that you wanted to build, and you said, well, I want to build 3 shelves and I have 6 bricks for each shelf, so then it's going to cost me, or I'm going to need so many supplies. So this would be another example of a linear relationship. And in science, we have things like the spring force. The more that you stretch a spring, the more force it takes to stretch it, right? So like if I stretch it just a little bit, it's a small amount of force, but if I stretch it a lot, it's going to be a lot of force. So this would be a linear relationship as well. And then if you pull it too far, then it breaks. So there is just a linear part of the graph, but that's another place where it could be used. Okay, so linear functions are important. They're used in a lot of different things. So what we're going to do is learn the tools that it takes to be able to use these linear functions in a lot of different ways. So we like to use variables. Variables allow us to, like with the distance equals rate times time, we can put in any number that we want into these slots and find out a new value. So we want to be able to manipulate these functions in many different ways. So these 4 main ways are the ways that we look at linear functions. So one is the verbal. So we say, well, it's a line with a constant rate of change, little a, that has an initial value of b. That might be a verbal description of the line. So you might say, well, it has a rate of change of 60, a constant rate of 60, and an initial value of 0, like you start at 0 miles. But if you had already driven so far, then you might have an initial value there. Numeric, so we want to be able to make a table of values. So like at any given time or at any given radius with one of these, at any given number of minutes, what is the cost, what is the total perimeter, and that kind of stuff. So this is a numeric representation. So if we can plug in values and get values out, this is how the function works, right? So we've been doing a lot of that already. The graphic, we want to be able to put it into a graph so we can see actually, where is the initial value? When we start out, where are we at? And how does this change? What is the rate of change? So how does this slope look in the plane? Or is it going down? Am I decreasing as time goes on, or am I increasing as time goes on? So that's another way to look at these functions. And then finally, the symbolic. So if we can write the rule, then we can have power to be able to plug in values and find out what is the result when we have 3 hours. So like here we put in 3. What do we get? We get 180 is the distance. So that's another way that we can use the functions, is using the symbolic representation of these linear functions. So this is kind of the big picture of what we want to be able to do. And if we're given any one of these, we should be able to, so if we're given the graph, can we come up with some values that make it true, right? So where are those points on the graph? Or if we're given the symbolic representation of the function, can we turn it into a graph? Or if we have the graph, can we explain what it is in terms of words? Or if we're given the line in terms of words, can we turn it into the symbolic? So going back and forth, there's a bunch of different pathways that we need to be able to transform these functions back and forth between. And if we're familiar with all these different forms that the graph that the function can come in, then we have a lot more flexibility when we come to solving these kinds of problems that occur in our world all over the place. So no matter what job you're going into, you're going to be doing something related to this. Even if you don't have a career and you just need to do your own taxes, you're going to need to be able to understand how to manipulate these linear functions. Okay, so that's the vocabulary. We're going to jump into a couple of exercises and see how we do with that.